It's chapter 5. I asked them to be in today.
You never gave us an actual answer.
But how many did you want to be?
I want Joe to turn in as many as you can.
Not exactly.
From 1 through 6 or something, you gave us 1 through
Right.
whatever you gave us, you wanted as many to be turned in today.
Yeah.
Okay. If anybody wants to work on lab 3, I'm down, because I haven't finished it yet. On that number system.
And I know I didn't give these out. Somebody else had the lab book, so I didn't give it out. So we're going to be really, really slack. But we'll have to make a due date soon, right? You understand that? And I'll go back and look at that because I've had people come in, and I think I told you about this. They'd come in the last day of class and turn in all their labs, and so we'll probably have to make a due date when we get into actual lab. The due dates will be specified according to when you get through the last circuit. But all these homework labs, we usually post these on the calendar when they're due. But the problem is that we had quite like 5 people that didn't get their lab book. Let's try to make them due by Monday, okay? And I'll go ahead and post those on the.
All the ones you gave out, by Monday?
Yeah.
Midnight?
No.
That's on Monday. You mean Tuesday? What's today?
Tuesday, yeah. Tuesday, sorry. So let me do next class period. It'll be Tuesday.
So Monday at midnight.
Tuesday. Next Tuesday.
We're not having class Thursday?
Huh?
We have class Thursday?
Yes, we do have class Thursday, but I'm going to give y'all until next Tuesday.
Next class day. My bad, y'all.
Tuesday?
I'm sorry, y'all.
No, this class, I do that all the time,
I'll
guys.
shut up.
That's why I put alarms and everything on my phone. So we okay? Next Tuesday at the start of class. Yes. Symbols, of course, diagrams deal with symbols. So we're going to be doing a lot of drawing in this class.
Wait. Labs 1 through 5. 1 through 4. 1 through 3. You say 1 through 3.
No, I thought I gave out up to 6-1. Didn't
I don't know what you gave
I?
out.
They're all
Came
up
out through
here.
6-1.
6-1.
1-1.
Well, I didn't give them out. I put them up on the table and I said y'all could.
Well, I had chapter 6.
Well, it's not chapter 6. It's just lab 6.
Yeah, I thought it may have
I
been.
believe you might be right.
6.
I didn't know that.
Pretty much they grew up.
So when we get into these, but you're right. You're right. I think you're exactly right. So that's what we're doing today. We're doing the 5 and 6. We're going to try to do 5 and 6. So what we have to do is when we get into print or diagrams, no matter what trade you're in, we need to be able to represent things besides drawing them out. So in the motor controls class, we go over all the different types of diagrams, and one of them is called a pictorial drawing. And this is if you go out and buy a new TV or something, since this is something that's put out to the average consumer, and they show you how to hook it up, they draw all these pictures, right? You understand? Show you how to connect things. When you start getting technical, those things eat up a lot of space. So what we start doing is we start representing things with symbols in our drawing. So just about all your technical drawing, whether you're in air conditioning, whether you're a welder, whether you're almost any trade, when they tell you how to do things or draw it, they do it with symbols, right? You understand? So we have to learn symbols. So normally we do this in what's referred to as a line diagram or a ladder diagram. Most popular do that, and it's just a bunch of symbols made up of drawings, made up of a bunch of symbols, but following some type of industry standard on how it should actually be drawn, right? You understand? And we've already looked at a little bit there. Creating relay logic using standard relay logic rules, place comments on those relay logic devices using standard rules, create relay logic for processing industrial controls. Sometimes called an elementary diagram. I've never heard it called that. Two things I've heard it called is either ladder diagram or line diagram. You can see how it got the name ladder diagram because it's got two lines that run on the outside, and we call the individual circuits, we call them rungs, right? Just like the rungs on a ladder. I've never heard it called a relay logic diagram, and I've never heard it called a elementary diagram. From here on out, relay logic diagram, we're going to use ladder diagram. First step is to do what? Create a program for a PLC. Well, that's not it. Show the symbols for different input and output classes. So what we got all these symbols. Now the only symbols we're going to start off with is basically go ahead.
I was reading about this yesterday, so it does say in the book that there is a ladder logic diagram and that there is a relay logic diagram, one being written first and the second being what you actually see on the screen. And I think that's kind of what it's saying here, because now it's saying after the relay logic diagram, which you just said we will not call it that, after it's drawn, it is converted into a PLC ladder logic diagram. Am I making sense?
Yeah, once you,
So that's going to be
we either do one or two things. Sometimes we have a relay logic diagram that we convert over to a PLC diagram. Sometimes we have a PLC ladder diagram that's never in electrical diagram, never in electrical diagram. What we do though is we have two drawings usually that's associated with a PLC. We have the drawing that is actually the program, which use nothing but symbols that's available in the PLC program. And then we have what we call the diagram where we actually show the electrical connection of the input ports and the output ports. That's where we use the symbols that are used in electrical controls.
the same thing.
Huh?
They're called the same.
I don't know.
Thank you.
I guess it would be. I've called it a wiring diagram or voltage between the rails. So we call these rails, right? You understand that? Are labeled L1. They are generically labeled L1 and L2. When you get into actual diagrams out in industry, how many L1s and L2s do you think you have? Okay, so what they do is they usually end with an L1 or L2, but usually they might exceed it with some type of letters. They might call it PCL1 and PCL2. And this gets very confusing in motor controls because we got an L1, L2, and L3 over here, which are 208 volts. And then we got an L1 and L2 that's 120 volts. And what happens all the time is people want to use that 208 volt for L1. So we started in motor controls calling our control rails CL1 and CL2. So what we've done is we specified that L1 over here in 208 volts is not the same L1 over here on your control. So when they say they are labeled L1 and L2, it's going to probably be something kind of different, right? But usually L1 and L2 is part of the name. It usually ends on that. Each row, and this is not exactly true either, each circuit in the relay logic diagram is called a what? A rung. I don't know what the book says. But it starts out doing single element circuits. It has no parallel devices and everything like that. But we know for a fact that we can hook outputs and inputs in parallel, right? You understand that? And as soon as I do that, I'm gonna have a different line. A relay logic diagram can have more than one row. So we got to get these names. And what we're going to do is we're going to use the nomenclature of what we use in the actual electrical diagram that we simulate with a PLC. So we're going to make some modifications to what the book, because the book does do some things that's kind of confusing. So this is so right now, this right here is a run. this right here would be a row, this right here would be a row. Okay, so right now, we have two things. And what I've done on the left-hand side, what the PLC does that we do different in motor controls is in motor controls, we number line numbers. We don't number rungs. In PLCs, they number rungs. Okay, y'all understand the big difference. A line is any horizontal line that connects somehow to the main line. So this is the main line right here. So these are lines. So right now, and what we do is we number line numbers. In PLCs, what they do is they give us run numbers. Now what we do in a true ladder diagram using relay logic, what we do is we have two things. We have on the left-hand side of L1, is what we call the line number. On the right-hand side of L1, which this guy did, but he did it incorrectly, we have what we call the numerical cross-referencing. And what this does is this shows the location of the contacts that are being controlled by the relay. So right here, this guy right here is in line 1, or in rung 1. So I would come over here, but where's its contact at? So I'd come down here and put line 2. And then I would come down here and put what? I'd put a comma, and then I'd put a 3, indicating that's where the contact's at. So in relay logic, we don't deal with rung numbers, we deal with line numbers. If I was to come down here and draw another something in parallel, like this, these two, since they're in line with each other, is considered to be the same line number. So what you do is, in your mind, is you physically try to do what? You don't do it, you just extend this all the way across. And any horizontal line that's lined up with this guy gets the same line number. Y'all understand? So now when I do this, I can reference things, right? So I can say, okay, go to line number 200. I'm not saying rung number 200. I'm going to line number 200. And we just get on the left side, we fall down and find what? The line number. And then I come over here and I see a relay. You know, on the right side it says 2, 5, 20, 50. Then I know where the contact's controlled by that relay. I know what line number it is, not what rung number is. Because a rung might be this long right here, right? Because we could have 15 parallel contacts. We could have all kinds of stuff. So this guy's kind of looking at the basic diagram that he puts on, I forgot what page. When he sets his rules up, he sets his rules up for this guy over here on page 90. Figure 5-4. That's when he starts talking about his rules. Now notice all these are single line rungs. Y'all see what I'm talking about? And you might run into those and you might not run into those. If you don't have your book, then you probably need to get by somebody that's got one. So this is the symbol for a push button, normally open push button. So when we talk about normally open, we don't spread it out. We put NO. It's supposed to be in uppercase letters too. It's not the word no. And actually, it's a momentary contact push button. So what do you mean by momentary contact? It's spring loaded, so you press it as long as you got your finger on it. It makes the contact. As soon as you let it go, then it breaks it. Now this is drawn real big. Usually we don't do it that big, but what we do is we come over here and we give our relays a name. So this is wrong right here too. So we give these things a name. So what they've done here is they put the name inside the coil. If the name don't fit inside the coil, then they'll put it down at the bottom, right? You understand? And then what they do, all the contacts that's controlled by that relay have the same name. And so that's what we're gonna do in PLCs. They call it symbols. Siemens call them tags, which is the same thing. So this is where you go in and you assign these things a name. And then from then on, you can reference it by name instead of referencing it by address, right? Which is pretty neat. I think I told you that. So this is what we call a normally open contact. This is a true contact. Y'all understand contacts on a relay now? Everybody okay? Yes or no? So this is a normally open, and we call this a contact. This is the symbol for a solenoid. And what's a solenoid? Didn't I show y'all that? Didn't I show you the solenoid? Did I put my little roller there, put my nail on it, and suck the nail up in that thing using the magnet? That's a solenoid. So a solenoid is a device that uses a magnetic field. So it's an electromagnetic device. So it uses the current flow in a conductor to create a magnetic field, and it causes a metal rod inside to move. And what do we use those things for? Yeah, like I said, you got a dishwasher or you got a washing machine. What turns the hot water on and what turns the cold water on? It's a solenoid. It's just got a plunger, and so what it's doing is opening and closing a valve. You ever walked in one of them doors where they got a buzzy in? Solenoid, right? That's a solenoid. So this is a device that takes an electrical energy and converts it over to a linear motion, straight line motion. And that's the symbol for it there. In relay logic, lines are numbered and not rungs. A line is any horizontal line. And I should put a little other phrase out here. If you got if you have two horizontal lines that are in the same plane, then they get the what? The same number. Are we okay? 9 rules. So we're going to modify these rules too. This guy, he does okay later on, but he screws up right here on rule number 1. Input devices are placed on the left corner of the room. This means that the switches, push buttons, and contacts are placed on the left corner of the room. So I don't know exactly, but this should be stated that input devices are connected between L1 and the room load, or loads. So this right here should be in parentheses. Since input devices can be connected in series parallel or series parallel, some of the input devices do not connect to L1. Y'all understand that? Yes or no? So I come over here. So I come over here and do this. So I come over here and do this, and I put a push button switch right there. And I come over and put a push button switch right there. Well, this guy right here connects to L1. This guy right there don't connect to L1. Right? You understand? It connects to the previous switch. I come down here and do this. That doesn't connect to L1, right? You understand? That would be a parallel. That would be a parallel connected contact. So we might have it when they say the upper left-hand corner. That's up here. What if this guy's down here in line 53? Right? You understand? Well, all we know is, and this is always true. All your input devices are going to be connected. What? Yeah, between L1 and the load. Between L1 and the load. That is true. Now, L1, we're using that generically, right? Because it could be CL1 or PLC1 or something like that. And when you get into big control, they had and I meant to run this off. I was going to give you, I'll show it to you, an actual diagram using industry standards from US Steel. And this guy right here was, good gracious, 200 and something pages long. I mean, we're talking about size D prints. I don't know if you've ever seen a size D print. Big guys use.
11 o'clock break.
Yeah. Let me get my train of thought. Get my train of thought. Let me finish my train of thought. So, in fact, you probably just made me do. So,
Sorry, I thought
Size
we was in
B.
between when we started talking about the diagram.
so what was I saying?
5
Huh?
USD.
Yeah, so what US Steel did is US Steel modified this a little bit. So what they did on their line numbers, they would start off with a page number. So they put 200/32. And what that would do is it would allow them to repeat numbers on a different page, right? Y'all understand that? So but this is the same basic rule where the line numbers are on the left, the what, and then the reference numbers are on the right. So the reference numbers also included a page number. If it wasn't on the page that you were looking at, then they would put a page number dash. And like I said, I'll give you a copy. Now you have to think about it.
Page, then the line number.
Yeah, and that's what US Steel. Now if that's standard, I don't know. That's the first. These
That's what they do.
were surely enough measure. So in the book they give you two examples. They give you one that's right and they give you one that's wrong. So what's wrong with this?
Put the after the load.
Yeah, they got the input over on the L2 side. This is not a good rule too. But one and only one output is placed on the right corner of the rung. This means that one output device, such as a motor, a pilot light, or a relay coil, must be placed on the right side of the rung. That last statement is true, but that first statement is wrong. So this is the way this is going to be reworded. Loads are connected between input devices and L2 with only one load per line. How many loads can we have per rung? Many. That's all you said, many. There can be only one load. There can be one or more loads per rung. However, multiple loads can only be connected in parallel in another line. Y'all understand that now? It's terminology, right? Everybody okay there? Yes or no? When a manual or electric motor starter is the load, overload contacts may be connected between the motor starter and L2. We have a problem with motors and overcurrent protection devices. So an overcurrent protection device, like a circuit breaker or like a fuse, is set to blow at a certain current, or pop or blow, whatever you want to call it. The problem we have with motors is when they stall or when they start, they pull between 6 to 8 times the run current at the instant they start. So we've got these motors over here. They're rated at, I think, 1.6 amps. And we got 10 amp fuses in our disconnects. But if you ever try to start two motors at the same time, it blows the fuse. And you say, well, that's only 4 amps, but they draw 6 to 8 times their starting current. So what we do is, let me see if I can find a motor chart. This is a reverser. So what we do is we use things referred to as overloads. So what we can do is we can fuse our circuit breakers to allow the motors to start, but if we allow the motors to start, if they ever stall, they would burn up and the fuses would never blow. Y'all understand that? Everybody okay? So what happens is that when you look at the nameplate on the motor, it don't give you the start current. It gives you what we call the full load current, which is how much current that motor should draw when it's running its rated load. When a motor starts, rule of thumb is that it draws between 6 to 8 times its full load current.
But that goes from the side, the side, the forward, the side, the building.
The difference in percentage is that's rule of thumb. Most of your small fractional horsepower motors draw more, but it's not usually a big concern if you follow the rules of NEC, which says 125% of full load current. So if you fuse according to that, the problem we get in, I'm starting a 200 horsepower motor, 746 watts per horsepower. That's a lot of current. 6 to 8 times that is not going to be within that 125 limit that we set on the circuit breaker. But the problem is your fuses have to let the motor start. So when I size a fuse, if that thing takes 1,000 amps to start, then my fuses are going to have to be rated at 1,000 amps. Because if I don't do that, what's going to happen every time I start the motor, it's going to blow the fuse. So what we have to do is we have to fuse them for their start current. But what happens now if the motor stalls or if the motor don't start? The fuses would never blow because when they stall, they're going to pull their start current. But your circuit breakers have been set to do what? Allow it to start. So what they had to do was come up with some type of method that we could sense overcurrent over time. So we let the motor start, but if the motors don't start, then we disconnect the motor. Okay. And we call these overloads. And unfortunately, I didn't hook up my camera again. I'll use mine. So we have overloads. These can be electronic overloads, which are very popular now. The ones on this one uses heaters. So what does heaters do? Well, heaters take a little time. Electric heaters take a little time to heat up, right? You understand? So these ones that I'm showing you here, these are using heating elements. These are still very popular because, number one, they're really cheap. It's just like fuses. Why don't everybody go to circuit breakers? What advantage does circuit breakers have over fuses? You can reset them. What advantage does a fuse have over a circuit breaker? That's exactly right. And usually they trip faster. So you get out in the industry, you're still going to see thousands of fuses. You get into your house now, you don't see many fuses. Most of them use what? Circuit breakers. But you go to Lowe's and buy a 15 amp, 250 volt fuse, and you buy a 15 amp circuit breaker, single leg circuit breaker, and you're going to be talking the difference between $1 and $15, huh? Yeah. Okay. So what they did, so we still see a lot of these. These are heaters. So this is the heaters right here. So what happens is the motor current that's being pulled by the motor actually goes to these little heaters. These heaters heat up a sensor. It's really neat. And then if it gives time, so if they heat up, which takes a little time, then it'll disconnect the motor. And then this little light, this little indicator right here will turn red, and this right here is where you reset the overloads at. Huh?
Are they acting like a timer? Or
Basically, but they're not. It's just a heater. So I got an electric heater in my house. I go and turn it on. What happens? Does it heat up instantly? No, it takes time. So automatically it takes time. So what it does, it kicks the motor out before the motor burns up. But it allows it to do what? Huh?
like a predetermined time?
Yeah, it is a predetermined time because of what size heater. So these heaters are set in there and you rate them according to the full load current of the motor. So so you say, okay, this is the full load current, and then the heaters are going to let what? 6 to 8 times come through. Now, this is not what disconnects it. These are the sensors that sense the overload. And then we have a contact in here that we put into our ladder diagram to disconnect the motor through its control circuit. Well, that symbol is the only thing in electrical controls that's allowed between the load and L1 is the heater contact. So if I was to come over here and draw the actual diagram, and, this is all covered in the other chapter, but we'll just talk about this just so you will understand this. Now we have no overloads in the PLC program. So what we're doing is we're talking about the actual electrical program now, right? You understand the actual electrical control program. So this is the way the wiring diagram would be drawn for the motor. So I'd come up here, and then we would put these big contacts up here. And right now I'll just call them M. And this is the power circuit. And then I would come down here. So this is the symbol of a three-phase motor, and we can call it anything. I got it drawn wrong. Hold on. It's close. And these are the symbols for the overload sensor. So there are these backwards C's. And then this would be the actual motor right here. And this is the symbol, that's the symbol of a three-phase motor. That's it. And over here, these would be my big power lines, my three-phase over here. Now this is the power circuit. Over here in my control circuit, it might look like this. So I would come over here, and I'd have this, and I'm going to label this stop. And then I would come over here, and I would do this. I'm going to label this start. And then I'm going to come over here, and I'm going to call this relay M. And right there, I'm going to put this symbol right there, and that's the overload. That is the on. And so when this thing right here, so this is M. This controls these contacts over here. So this is my control circuit. This is my power circuit. And any of y'all guys in HVAC, you should be familiar with this. So if you ever look at the panel, it shows you got two diagrams. You got what we call the wiring diagram, which shows you the power circuit, and then you got the control circuit that's got all your electronics and stuff over there. So what happens is that I come over here, and how does this work? Well, I press this button right here. It closes this guy, energizes M. So what I'm going to do, I'm going to come over here, and I'm going to put this indicating that contact right there closes. Then what can I do with my start button? I can release it because we sealed it in, right? You understand? But when that closes this contact, these contacts over here are the same name, so what's going to happen? All of those are going to close. Now the motor comes up and runs. But let's say the motor stalls. Well, if the motor stalls, that comes up here and starts heating these things up. If they get too hot, what does it do? Opens that contact and kicks out the motor starter, and if we kick out the motor starter. So the only thing that's allowed between the load and L2 is overloads for a motor starter. That's the only thing allowed. Nothing else is allowed between L1 and the load. Between L2 and the load. Y'all understand that? So normally in electrical controls, we have two circuits. We have the power circuit, and then we have the control circuit that's controlling that power. And what's neat is this over here could be 660 volts, and my control could be what? 26. So which is neat. And why I put 660, that's one of the voltages they had out at US Steel. I think it had 120, 240, 440, 660. And I think they had a 6600 volts up there too. That ran the big blowers over on the blast furnace.
So you did say the only thing allowed between L1 and L2 is the overload?
It is an overload for a motor starter. You just can't stick a overload anywhere. It's going to be the overload that belongs to this relay. So this relay right here has a name. This is called a magnetic motor starter, electromagnet. Most people just call it a magnetic motor starter. So these are the contacts. They're all sealed in. So up here, this would be L1, L2, L3. These are our power. And down here, these would be what we call T1, T2, T3. This is where the motor actually hooks in. And all these other contacts, we call them auxiliary contacts. These are contacts that don't have to handle power. So that would be stupid for me to use a contact that's rated at 500 amps for a seal-in circuit. So your motor starter has what we call auxiliary contacts on it. These are very small contacts. This you can really see. It's this guy strapped onto the side right here. So this is a low current contact. And so that would be an auxiliary contact that we could use inside the control diagram, and it would be low voltage. Anybody want to see the motor starter? Now we have no overloads in a PLC program, so you'll have to take care of this out in your control circuit, right? You understand? Your PLC is not going to run a motor normally. It's going to have to be a little tiny thing, a little like fractional horsepower motor. So my little motors over here are these 24-volt motors. The PLC can run it, but the PLC cannot run a three-phase motor. But what can the PLC do? Pick up that guy, right? So we would hook this up to an outlet, and then that guy would run it. But then we would take care of the overloads out there. So what we're doing now is we're talking about electrical control diagrams, and we're not talking about the actual PLC program. So this is illegal, right? Well, they tried to do. Can't do that. You can attempt it. In fact, in motor controls, we actually do this on purpose. There's one of the labs you do on purpose to actually you can see what they're doing. And what happens is your relays might pull in the thing that holds it. Cause all kinds of things. And we put a light in series, and the guys say, well, the light's not coming on. Well, the light's not developing enough power to come on. So everybody okay on it? Yes. If you've got a magnetic motor, if you've got a motor that doesn't have overloads. Now a lot of your motors that are we call them in industry, we have multiple voltages available out there. And of course, the higher the voltage, the less current's required to produce that horsepower, right? You understand? So we have what we call multi-voltage motors. Usually they're dual voltage motors. And what we do is we literally rewire it to run on a high voltage, or we rewire it to run on a low voltage. So what that does, it allows the plant to have one spare motor that actually can run on two different voltages. Well, what happens is that your overload size is dependent on how much current you pull. So what happens if you wire it for less high voltage, the motor needs less current to produce the horsepower, right? You understand that. If you wire your motor for low voltage, it requires more current. So what they do on these motors is the overloads are going to be external. So this motor starter that you saw here, this motor starter is designed to run a dual voltage motor. So what that means is I can change the overloads out on them for different motors. Now, what's nice about solid state overloads? It's going to have a little wiper on the side that you can do what? You can change the electronic overloads. We don't, but these heaters, we'd have to change them out for a different motor, or we could use the same overload, but we use different heaters for different voltage motors. If the overload is in the motor, and this is required by OSHA, that if a motor's over like half a horsepower, it has to have a overload. A lot of your single voltage motors, the overload will be in the motor. And if the overloads are in the motor, then you don't have to use a magnetic motor starter. You can use what we call a contactor, which is just a big relay. Does that make sense? So all your motors in your house, does those have overloads in them? Yes. Where are they at? In the motor. And those use a little thermal switch. The overloads are thermal switch, so if they kick off, they automatically do what after a little while? They'll automatically reset. So if you got an HVA system, you're not going to see any overloads on any of the motors out there, even on your compressor, because the overload is inside, because it don't need different overloads because it's designed to run on one voltage, right? Some of your single phase motors will have a little red push button on the side where it's got a mechanical overload in there and you have to reset it. But all your house motors will And a lot of times when the motor goes out, guess what's wrong with it? The overload's bad. And you take that thing in, you swap it out, and they send it down to Chancey's or someplace like that, and what do? Take that away. I'll pass this around. This is actually the stator off a three-speed motor. And this big old, see this big red wire right here? What do you think that is? That's overload. So that one's in, that's in. Eric's gonna be up here. Get my workout for you. That's pretty much well solid iron, and it's got a lot of copper.
Thank you.
Input devices may be connected in series, parallel, or a combination of series, parallel, right? Everybody understand that? This does not make it a parallel or series circuit. What makes it a parallel or series circuit depends on how you connect the loads, right? Well, I don't have the slightest idea what's wrong with this guy right here. Unless they're using the wrong symbol. That is not the symbol for a light bulb. This is the symbol for a luminary or light bulb. Here they got the switches in series. And of course, so how many lines would this, how many rungs would we have? Two. How many lines would we have? Four. Four. Good.
Go back to the last slide.
Now this is rule 3. This is right in the book. Okay, we're okay? Only parallel, and this is true. Only parallel output devices may be placed on a rung, so that's true. So this basically contradicts what the guy said in Rule 1, right? Or is it Rule 2? Are we okay? So this is okay. So how many lines can a rung have? So I went out there and I put the lines out there and took the rungs away. So in electrical motor control, we don't deal with rungs, we deal with what? Lines.
Do you think that it meant branches? I've seen them use the term branch. So it's different.
I've never heard it called a branch. In a parallel circuit, we call it a branch. Okay. So we say but then when you get into house wiring, they call everything hooked to a circuit breaker, they call it a branch. So.
But in PLCs, it's still.
In DC, every parallel device, we call it a branch. So what is a rung? A rung is a complete circuit that runs between what? L1 and L2. A rung has to have at least one line, it could have both lines, right? But we have one primary line, and it's going to be the line at the top. So when we go parallel, by the way, we don't go up. We always do what? Drop down from your original line. So we start off with an original line, right? You understand? And then we drop down from that. Now your PLCs are going to do kind of something a little strange. Is that you've only got so much display space on your display. Well, what happens when your run gets too long? Well, what it's going to do is it's going to come over here and it's going to put it kind of an S shape like this. But all that is the extension of that line, right? You know what I'm saying? And that way you get another line number. That's just the way the PLC does it because it don't have enough room to put everything in the run. Or in the line, I should have said that. While input devices can be represented multiple times in the relay logic diagram, each output device can only be represented once on the diagram. So represented means once we assign that sucker a name, right? You understand? Then everything else has to have a different name. PLCs lets you repeat rung. So you can repeat outputs, you can do all kind of, we used to do a trick, used to when the PLCs first came out, the scan time, how long it takes to go through the program. So a scan time would be, okay, a scan consists of the PLC program, the PLC reads the inputs, runs that through your logic, then updates outputs. And that would be a scan time. Used to, the scan time was so slow, if you had a relay, if you had 200 or 300 lines, it would literally miss inputs. Because if you hit that button and released it when it missed the scan. We don't have that problem much with the speed and the processing power we have in our PLC now. But we used to repeat rungs. So we'd take this same rung up here and put it down here. Everything was exactly the same. And what it did, it would make it scan it multiple times. But we usually don't have to do that now, especially since your PLC support what we call interrupts, which we'll talk about in the PLC. So here they're using switch 1 twice. We can't do that in ladder logic. We can do that in PLC logic. Y'all understand that? And that's what the guy's saying. So switch 1, they're given two different devices the same name. You can't do that in electrical control. Are we okay? All the inputs and output devices must be placed horizontally. This means that no vertical position inputs or outputs are allowed. So this right here is not allowed. That's true. But we don't draw any symbols vertically. They're all drawn horizontally. We can do this. Huh? Right. Well, yeah, what it would give? It would give us two methods of turning the light on, and two methods of closing the end. So the signal flow would come up here. If this was closed, we'd go that way. If this was closed, we'd go that way. So this switch right here would turn on both these devices if that was closed. If this right here was open, we can implement this, but we'd have to do it a little different. No backward signal flow, current, and this is what they're talking about, current. This guy right here has a problem. He don't understand that L1 could be minus, L1 could be plus. If L1 is minus, then L2 could be plus. If L1 is plus, then L2 could be minus. We could put AC on this thing. What does AC stand for? Alternating current. What does that mean? One time it's flowing between L1 and L2. The next time it's flying between L2 and L1. So we don't talk about current. We should talk about signals. Signal flow is from left to right. And that's what I've said. Since AC flows in both directions between L1 and L2, can be either negative or positive, this should state that signal flow is from left to right, or from L1 to L2 would probably be the way I would like it to say. Are we okay? So current. Signal flow, the signal flow is from left to right. And that makes this next rule make sense. So this is illegal. This is illegal in PLCs. This is illegal in motor control. We cannot backflow. We can't make the signal go back to the left and then come back to the right. If you're going to do it, it's going to cause all types of problems. It also creates problems with people trying to figure out what goes on, because now you got something that's going backwards, which they don't anticipate, right? You understand? So people that work from electrical control don't anticipate the signal going backwards. So this is why we teach industry standards, how we do something in industry. Because sooner or later, somebody's going to have to come back in here, and hopefully they can come back and understand what you did. Or you might come in 2 years later I don't know if anybody's ever done that. Saying, what in the world was I thinking about, right?
Yeah, we've had this happen in.
Diagrams must be numbered and commented correctly. Rung numbers are placed on the left side of the rung. That's not true. In PLCs, that is true. What's on the left side of the rung? The left side of L1. So it's not left side of the rung, it's the left side of F1. These are going to be line numbers. Instruction symbols and comments are placed above the instructions. Rung comments are placed to the right side of the rung, that's true. I don't know what he's talking about instructions. We don't have instructions in electrical control. It's not a computer. Is that what the book says?
It talks about instructions, and instructions being
More
your,
results than it is instruction, man. It's turn on motor one.
Well, it's more functions than it is instructions. So usually
it
when you
refers to your mobile web and contact.
it is in PLCs,
Not on the diagram?
not on an electrical control diagram. It's going to be a push button. It's going to be a function,
Oh,
right? You understand?
You said you word that first.
This one should say what?
the numbers and things on the left side of the-
Yeah, line number's good. Yeah, exactly right.
Like, I know, like, I did that, and line numbers, but like.
It's gonna be line numbers too.
Somebody might call it up.
You just have to deal with it. You run into that all the time. So what we're doing is we're teaching the industry standard way of doing things. When you get into a company, you need to adopt the way that what they use, right? And you'll get into companies where they don't use industry standards, unfortunately. About the only industry standards they might use is maybe OSHA standards. But if you get a company that does electrical controls, then they're going to do it according to industry standards because they're selling their equipment, right? You understand? And when they provide you the diagrams are going to be according to industry standard. I think I told you about Dan Steele, right? The guy at US Steel that did all that work and didn't document anything.
Made all that money off
He didn't, I'm sorry, I can't say he didn't document anything. He didn't give US Steel the documents. But they let Dan do whatever he wanted to, and he was sharp. I mean sharp. And we had a couple of guys out there too. He was. Dan was a genius. And I don't know exactly what they mean right here. So what we do, and what I'll try to do, I'll try to get my printer working down there. Right now I can't do it, is to actually do a true electrical print so you can see what we're talking about. Normally, what we're trying to do is we're trying to make these things extremely easy to wire. So if I go out there at my car and I start looking at wiring harness, what do you notice about every wire? They're not, cars we don't label, they do what? Color code. So that means when we wire them, they wire it according to a color. Well, this would be what they're talking about that we would place above the line. We would write what? The color of that wire. And then I can go up there and when I'm wiring this thing up, instead of me trying to use an ohm meter or something like that to figure out what wire, I would just do what? I'd go through my bundle and I would find that color. Well, this is what they're talking about here. So what we do in electrical control is we somehow identify the actual wire. We either do it by color, which is very, very popular in automobiles, or if you get into an electrical thing out at like a big company, they're not going to use colored wires. Why? Because it costs a lot of money. So here I'm wiring something up, and I got to have all this red, all this green, all this striped wires, and all these other colors. You get out at a big company, you're going to walk in there, and it's going to be all the same color. Every wire is going to be the same color. So what do they do? How do they identify the wires? Anybody know? They'll sign them up. number. They'll sign a number. And at the terminal board, they'll have the number written on there. So normally in electrical controls, what do they write above the top? They write the what? They write the wire number. And what goes on the right? Comments goes on the right, that's true, but also we identify the location of the contact on that too. Yeah, we call it most people call it cross-reference, but the whole number is numerical cross-reference. If you looked it up. And like I said, I'll try to, we got a great printer down there, but for some reason it's not taking paper. I had time to go figure out what's going on. I don't know if I typed this or not. Line numbers are placed to the left. I know it's time for run. Line numbers are placed to the what? Left for L1. Numerical cross-reference numbers are placed to the what? Right. Wire numbers or color codes are placed above each conductor. And then wires that are connected together have the same number. This is true on electrical control. I've got the US Steel guy up here. If I can't run it off, I'll give you a copy of it. I can't do it today. Y'all hold on. Let me get Roe, and then we'll break for lunch.